Okay, starting with the recording. Before starting the new, just to comment about the first homework. That was okay, not so complicated, quite simple. Actually, at the end, doing the check, I didn't remember that Bose-Einstein was actually a little tricky at the end. It was nice to see the two behavior to fix it. Someone probably check for some information and put that okay, you are, at the end you have the g minus 1, not the g, and so it's g minus 1 to g because g
Oh
is
yeah, I noticed that. I find that that my answer was different from what I
no, but g
get
is
to.
really big. It's really big, so g and g minus 1 is almost the same. So you can approximate in this way, and you have the typical solution. Someone just hide the dust below the carpet, put the result. But okay, no, it's not a problem. It's actually it's just taking away the minus 1 because g it's this type of statistic is really big, can be really big. So they change. It's not it's small, and you have everything is just approximation. Because already using the Stirling approximation for the factorial, it's not perfect, but really good. So you can approximate or just
Professor, are you trying to share screen? Because we're not seeing your screen. Are you showing us something? Because you're not showing us.
No, because well, it's just calculation. Actually, it's as you see, you take, you change the factorial. Actually, the only thing is that if you check that and do the calculation for the derivative of the factorial, so putting all together, so doing for the Stirling approximation for the factorial and then the derivative, you see that the derivative of the factorial is just the logarithm of the argument. Because the other are taken away because you have for the Stirling on x multiplied the logarithm of the x minus x. But the famous and watermark logarithm derivative of x multiply logarithm natural logarithm of x, it's logarithm natural logarithm of x plus 1. So plus 1, then there is a minus 1, and throw away. This is just the only things that if you know, okay, you can be a little quicker, but it's not this complicated calculus. It's just quite linear. And but at the end, from that probability, you get your distribution is really nice with this peculiar properties do the plus 1 or minus 1. Okay. Talk about that. Let's start. Okay, let's start to sharing. Screen sharing. I send you by mail the slide, and you can follow on your screen with your copy. And also several pictures. Yesterday also send the PDF. You can, it's just to support. Now let's see this what are the nuclear reactions in a star. Not all, because there are several, but the main, most important one, the most famous one, the ones that are important for the life of the star. They are, and see the part that are also, and you can understand the change that you have in the life of the star. Something about notation. T with the underscore on below a number is just the temperature divided that exponent in Kelvin, because it's easier since we have a lot of high exponential. We are working with the temperature of 10 millions of Kelvin, hundreds millions of Kelvin, billions of Kelvin. It's easier, this notation. So we have T6 for the temperature in millions of Kelvin. Okay. This one, classical notation for an element. Here is the name of the element. Then in the upper left corner, there is the mass number, the number of nucleons they are inside the nucleus. And below on the left, there is the atomic number. That is, okay, the atomic number determine the element, so it's redundant actually, but sometimes it's useful just to see how it's changing in the reaction with among the two, because not always you remember all the atomic number of all elements. Then we usually approximate, not equal, but the energy production per unit mass in this way, a constant multiply density to the exponent and the temperature to the non-exponent. Actually, the real formula are really more complicated. A real mass, you usually have an exponential with inside the temperature or something else. And actually, these two coefficients, to show in this briefly, are calculated this way. With the so similar for the adiabatic gradient. It's the logarithmic derivative among the energy production, the density, and the temperature. Actually, for example, the nu, you calculate the logarithm of the energy, of the formula. You calculate the derivative expected the temperature, and then multiply by T. This gives you can see that you have the exponent. In this case, it's exactly nu. In other, this trick allows you to have some exponent that is can be used for quick calculus. So just to understand how depend the energy with the temperature, the density. Mainly the dependency with the temperature can be really complicated. You have the T to an exponent, or you have an exponential inside the temperature. Sometimes you have fraction inside. So this is a simple way to obtain. Then just remember that the crossing section is an area, and usually calculated in barn. The barn is 10 to 20 minus 24 centimeters square. And as we saw, usually the cross-section is approximated as a function, not really well depending on energy, then divided by energy for the exponential of the node that we know. 1 year, usually that you can put the abbreviate with the Y or with the A of annus, the Latin. I put also this one because in some paper, some referee or editor that wanted the A because it's most standardized. Because it was the old way to the, say, giving the Newton measurement when there is in years, you should use annus, anni, in Latin, and put in A. Okay, let's start. Obviously, the first important set of nuclear reaction is the one connected with the hydrogen burning. And the most famous is the PP1. PP1 is most famous, most direct, because we are definitely starting with putting together two protons, two nuclei of hydrogen, but is also quite tricky. It's more complicated than what you can see. Usually, it's just put that you have an hydrogen with a proton, there is a beta plus decay, and you got the deuterium. And it's true, this is okay, it's something that can start with just above 6 million. The whole PP1 usually a dominant below 10 millions of Kelvin. You have for just this small amount, but most important things that is really, really complicated reaction. You can see here the S is 10 to the minus 22 kiloelectron volt per bar, more or less the temperature here are 1 kiloelectron volt. That means that the mean life is 10 to the 10 year. A pair of proton takes 10 to the 10 years to collide and produce the deuterium. It's a really long time. It seems terrible, but you also want to consider that 1 gram of hydrogen, 1 mole, is 10 to the 23. So with just 1 gram, we manage to have a lot of reaction. Why it takes so long? Why it's complicated? The cross section is so small because it should be the most easiest reaction since the Z is just 1. The problem is the spin. To form the intermediate compound not stable nucleus that is an helium-2, it's you need that you have 2 protons in the same level. They cannot have the same spin. They have to be antiparallel. So if the collision has 2 protons with the parallel spin, the reaction will go in the channel of scatter directly. If there is not little probability of the spin flip in the middle, but more probably that is just the scatter. You need the 2 protons have opposite spin, antiparallel spin, so you can form the compound intermediate nuclei of helium-2. Then the problem you need, since it's unstable, you can have just a breakdown, scatter, or you need to have the probability of a beta plus decay, so the proton decay in neutron and positron and neutrino. And protons are not so keen to do it. It's you need this also additional reaction. Then the problem is that you have a deuterium, but as I said, previously you needed to have the two nucleons with the antiparallel spin. Now you have a proton and neutron with antiparallel spin, and this position is not the most lowest energetic state. So you need another thing flip to be a little more stable and stay more bounded together. To go to the basic, to the lowest energy state. For this reason, it's the cross-section is so low. As we saw, the cross-section is not just the part of tunneling that the particle can enter in the potential of the other. Is not just the size, the classical part of the moon, but it depends also on the channel that you want to go outside. And for this reason, the cross-section is quite low because you need the right spin, pairing of the spin of the two spin, and then the beta decay, and then a spin flip to have at the end the deuterium. Then the situation gone more smooth. You have another fusion with another proton and production on helium-3. And this is really quick, well, just 1 second, with the production of more energy. Then what we have even more energy is the fusion among the two helium-3 with the production of helium-4, what we want, and we release the two protons with the release of almost 13 megaelectron volt. Here it takes more time. Obviously, we have helium-3 that is more. It's a Z atomic number higher, so it will more complicated. 10 to the 5 but, years, but we have enough time. At the end, the total Q value, the total energy released by the reaction, energy without the neutrino that is produced here, all the Q here with total is considered taking away the neutrino because they just go away, is an energy loss completely. To calculate this value, you have to remember that to have the third reaction in the PP1, you need to have twice the first two, because you have to produce 2 helium-3. So the Qt is the Q1, Q2, energy here and here, sum multiplied by 2, and then sum with this one. At the end, we have a total little more than 26 megaelectron volt, and if we divide for the final product, mass number of helium, that is 4, you have 6.6 megaelectron volt for nucleus involved in the fusion. Yeah. About this, you can see here. essentially, typically for the sun, and that usually it's just going with BP1. You have this just showing something obvious: production of in what is the concentration of hydrogen with the radius, and hydrogen above here helium. Obviously, you produce more in the center, and the hydrogen is depleting. This also shows you that in the radius, you have just that usually the core where you have the nuclear reaction is like 0.2, 0.3% of the radius. It's not a big part. Below, you see the fraction, the presence of the helium-3. You can see that it's really concentrated in one part. This is because you have some reaction that producing it and some reaction that destroy it. And essentially, in the end, helium-3 is completely destroyed in a star that have high enough temperature. Because, for example, we see in low mass stars that arrive of that 6 million of Kelvin to start producing the deuterium and start the PP chain, but have not enough energy, temperature to fuse the helium-3. So you are accumulating the helium-3 instead of helium-4 at the beginning. So you see, for example, this is essentially, you here are producing in the accumulation. In here, this is a complete depression of the quantity of helium-3. This one. PP1 is not the only one. Actually, it's the only one for the first stars. But not only, because helium there is always been helium. If you have enough helium inside the nuclei, when you start to have enough helium, you can have an interaction with among the two helium-3 and helium-4. PP2 is essentially the start is like PP1, but then helium-3 fuse with an helium and produce this reaction with beryllium, then lithium. The lithium take a proton and produce two helium-4. So at the end, the production is just helium-4. The beryllium, the lithium here is produced but quickly destroyed. It's at the end, the energy is quite similar. It's always a little less than the 26 mega electron volt. We have an additional channel, that is PP3, that start as before with like a PP2, but then you have a little different. The beryllium-7 doesn't. Here you have actually electron capture. An electron is absorbed by the nuclei. Usually, beryllium-7 try to do it with his own electron around the nuclei, but here obviously they are completely ionized. So it takes a little more time, but take it an electron, or you can get another proton, go to boron, and terminate the cycle in this way. This is quite quick. We'll see beryllium-8 is really, really, really unstable. And this reaction produces most of the energy and lose also most of the energy. In fact, the quantity of energy lost by neutrinos is 30% in this case. In fact, I have the lowest quantity.
Professor, which of these two reactions is more common? Because which of the two is more common?
I'm writing exactly these things. The different is usually we talk about PP, just PP1. That is because it's the main reaction above 10 million of Kelvin degrees.
Between PP2 and 3 that use the same atom to start the reaction?
It depends on the temperature. And obviously the presence of helium. More you have helium, more the start of PP2, PP3 are probable. But below, like the million, definitely it's are dominant the PP1. And the sun arrives a little more than 10 million, 13, 14. Among 13 and 23 is PP2, that is the principal reaction, and produce in the PP chain. When you consider PP chain, the PP2 is more probable, and you have this reaction for above 23 million start the PP3. So the difference is that you need a higher temperature, and so you have more one channel or the other accordingly. Actually, we'll see that PP3 and PP2 then are not so well common, but for another reason. We'll see with the next reaction from the introduction. But in the PP channel, proton-proton, you have usually with lower temperature of PP1, and then with higher temperature start PP2 and PP3. Please, I need to change. Thank you. Here, right. You see in here, the server production is at lowest temperature. You have PP1. Your lowest you have PP1, then are starting the PP2 here in the middle, and then for higher, the main production of helium is done by the PP3. This is according to the production for the helium for the PP channel. The situation is a little more different. Okay, because we have another guy before a little mention about some part. In general, for the sun, typical the production energy for each reaction is mean 27 megaelectron volt. The mean value is 6.5. The coefficient for the energy production for the temperature at with temperature of 5 million in more or less 6, then decrease a little, arriving to 30 million with 3. This is considering all the reaction, the PP chain in general. Theoretically, you could have also this one, the fusion among the helium with the proton, then a beta plus decay and in helium-4. But they check for these neutrinos that have a particular energy. It is not observed. So probably this reaction does not work. It's not working. Or it is working, produces so little that you cannot detect the neutrinos. There is also present about the first of the PP1, what is the proton-electron-proton, where you got you get the proton and electron. Instead of having a proton decaying in beta plus decay, you have the fusion, the inverse of the beta decay with an electron and production of a neutron and a neutrino. And this is observed, but yeah, 23%, it's really low. You can understand that you need an interaction with a third particle that is really more difficult to have it. This is, as we saw, the typical reaction of the sun, but then we realized that there are another reaction that if you have already in the stars some carbon, oxygen, or nitrogen, not necessarily all of them, but at least some of them, you can have the two famous cycles, CN and CNO, that is essentially these are just the catalyst for the reaction. There are several reactions entering one proton each time, and then the release of one alpha particle and helium-4 with this chain that everyone produces a little energy. This part it's quite interesting because okay, this produces energy, but of all the reactions, the most interesting is this one because at really long time, it takes the nitrogen 14 doesn't like to react easily. That is some part also because they are pair. When you see when then the number here and here are even, the atom is little less happy to interact. And so usually this is the slowest reaction. So mainly you have all the other happen quickly respect to this one, and this is the last one to react. You have a total production quite similar, 25, and this reaction is really important above 15 million. In stars where the core are hotter than 15 millions of the Kelvin, you start to have the CN cycle and production in this way. There is also the cycle with the CNO that have more use of oxygen, as we see, that they need a temperature a little higher, 20 million, but you can see definitely less probable, one every 2,000 or less, 3,000 times you have to decide. Also because you have more massive nuclei, so the atomic number is higher, more complicated. Produce at the end less energy, but it's quite similar. This is peculiar, it is resonant, and so and so. Oh, a little long. It's don't worry. Here you can see a little better the cycle. This is the main CN. Then you have the CN2, CN3. No one will ask you to remember this one. PP1, it's easy, so it's supposed that you know it. It's something that is supposed that everyone knows it. PP2 and 3, just it's supposed that you remember that you need helium to start, and there is the production of beryllium, lithium, and boron that is just destroyed after. So not a real production of this element, but just are destroyed. So if there is present, this element are destroyed, and you have the production of helium, and they are transformed in helium. This is quite complicated. You have this several cycle that, but this is really important. This one. Reaction mainly because you have this interesting result. If you are considering the abundance of this element in a star with CNO and a star without CNO, just proton-proton, you can see that you have a nice change in composition, because carbonium-12 drop, the carbonium-13 it's a little enhanced. That so if you check for the composition outside a star, you can see that the ratio between these two that have a little different line, because this is 12, this is 13, so little easier. So the line on for the metal have a little difference. It's well, there is definitely noticeable. You can notice the difference in the abundance, but mainly what you see that there is essentially a lot of nitrogen, because as I said, this reaction is really slow. So essentially all the carbon and all the other are thrown toward to be nitrogen 14. So this is really well enhanced, and the other are depleted. For example, the oxygen 18 disappear, and noticeable also oxygen 16 and so on. At the lowest, you can see here the production energy respect of the two. For lowest, the 15 million of degrees, it's the PP are producing definitely more energy, but increasing the temperature, the CNO is start to increase really more. PP is like more constant. This increase, it's clear if you see here. The exponent for the CNO are definitely high. At the beginning, it's 23, then is 16, this decreasing. This is why the reason, as I said, the nu is not exactly a perfect coefficient, so the temperature arrives with the coefficient they are. It's what you obtain with that calculation. Usually, mainly in this, from here, you have that the inside you have formula like exponential with the coefficient divide the temperature. So you have this value. It's like 23 divided by temperature, and so decreasing. But it's really high. You have, say, 20 as exponent. That means that you have a little increase of temperature. You have an enormous increase in the production, because it goes with the exponent. You know, if you're looking for the proportional increment, you just have to take the logarithm and to the derivative. So you have you need to have proportional increase in here. You have an increase proportional to like 20 times the increase in temperature. So if you have an increase in temperature 1%, you have an increase of 20% in the energy production. And this is the reason why I start. So essentially, it's the main energy production for the start. When the core start to be over the 15-20 million, it's CNO. This means start with mass, I forgot the spot, above 1.5 to solar mass, essentially F stars, exactly the stars above us. We have the G type, the F start to have more CNO than production than the PMP. And this is, okay, as I said, also a lower temperature, that we have a little, the starting, that at least they convert carbon in nitrogen. And nitrogen is stable, is there. And one point, obviously, these reactions are in the core, and the core is not connected with the surface. So technically, we cannot see change in abundance because of the CNO reaction. But as we saw later, star evolve, start to produce at the beginning helium in the center. When you have the hydrogen is completely depleted, the star move to the red giant branch, start to have some transformation. One of this transformation cause that you have a really almost all that most of the part of the atmosphere is we have a convection. As we saw, we have a nice energy transportation that have also a mixing. It depends on the parameter called the mixing length, that is the convection. The convection starts to mix the external part of the stars, but in some point we have a really strong production of more the production energy. So we have a really high increase in the center of the stars, but we are trying to go to the helium burning. And in this way, we have an increase in the temperature gradient, and we saw this causes starting on the convection. At the point, we have a really big convection. They are arriving just above the shell that is burning the hydrogen. So taking some part of the resin and bring it to above, and what is above back to below. This is usually more, this big dredge up, as it's called, is happen in asymptotic giant branch. The really advanced when already the star have already burned also the helium. That is a really good mixed. And you can see the result of the CNO on the surface. changing completely as you see here, the ratio between the carbon, the quantity of nitrogen, but the other on the abundance. This also permits to distinguish by spectra an asymptotic giant branch star with a red giant branch star. They are really near photometrically, but have this clear difference in abundance. So CN and CNO have two important facts. One, that is the main source of energy for stars above approximately 2 solar masses, with the core above 15-20 million Kelvin, but also is the reaction that will cause a little change in abundance when it starts. And we'll see later that this is also the main reaction also in the hydrogen shell. Is that one that is all most of the stars start to have a certain point. Not all because of the smallest are okay, problematic, but also the sun, when it started to have the hydrogen shell, will start to use the CNO because just below the temperature start to be higher. Please. Thank you. Yeah, 1, 2, 3. Yeah. Here you can see that it's quite interesting the evolution involving the chemistry of several products according to the difference change in the composition with hydrogen, with here the evolution and the temperature. You can see here mostly that at some point start to have is the jump in the composition in nitrogen that increase, but decrease. Here is 10 million already burned, but the other that start to drop down to the classic. This.
Profe,
¿Mm?
Raúl está pidiendo que si le puede aceptar, que se le salió. Por favor.
No había visto. Okay, if it happens that you are going outside, quickly tell to the others because it's the list of participants is on the other monitor. I don't look at a lot, so I didn't realize if someone was dropped out for some reason on the connection and is waiting to enter again. Okay. As we saw, this is I coefficient, as we saw, but is not the worst scenario. Now we'll see some others. Cycle for production of helium, hydrogen burning. They are not really important as energy because produce not so much the energy. It's similar, you're using a catalyst to do this with the change in, but the most part is this one. Like for CN, CNO, you have this change in abundance. Because essentially something that Jared and Raul here, probably, I don't know if also Macarena, the other. Usually when we are talking about stars in cluster to black cluster, there are several abundance, relative abundance we talk about, like the oxygen sodium relation, it is an anti-correlation, and magnesium aluminium. The reason is this one. Here we have there are two this important that is important for the composition. The first one is the neon sodium cycle. Neon sodium, it's, you see, 23 nucleons and 11 protons. It's even odd number. So this element is 100% only in this isotope. You cannot find the other, and in fact you have that. Okay, this is the 22, 24. Sodium 22 have a mean life of 2.6 years. Sodium 24 is just 15 hours. It's really unstable. In the neon sodium cycle, you have this one. And that the main part, you see, you have proton, 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 proton produced in helium, and start with neon 20 and stop with neon 20. But the most important is this one, because this element is quite stable, doesn't interact really well. So the concentration of sodium can be higher of factor of 10. You are really high. On that case, example, neon, that is an even number, it's stable all the three, 20, 21, and 22. Mainly is a neon 20, but the other is not, they are not stable. It's just they are less produced at the end of everything. The cycles start among 30, 35 million degrees, working better around 50 million. That, okay, is not a normal for the sun, is not so easy. But as we saw, the temperature can go higher, especially when it's burning in shell. And we can understand something. For example, this is responsible for the oxygen-sodium relation, anti-correlation. But obviously, how? Because you cannot see oxygen here. So how enter the oxygen? The oxygen entered with the neon, the production of the neon, but this is later, so how this can be correlated, because here production of hydrogen that can mix with the Rajab. The oxygen is the combustion, the burning oxygen is after the helium, after the carbonium, in a part that is not involved in Rajab. So how is this possible? The reason is the temperature. This cycle is working really well above 30 million degrees Kelvin. When you have, and it's working with hydrogen. So it's working where you have the abundance of hydrogen is high. It's not so an area where there's burning hydrogen. And if at the temperature, that is really effective, this is really well working, the CN-CNO cycle. that deplete the oxygen, as we saw. Here, we see that oxygen is very well depleted. Oxygen 16 is depleted, while here with the cycle that is in parallel because they are in the same condition, it's enhancing the sodium. So if it starts as this past this, then with the drop, this resin are brought to the surface, and then throw away took the surface and are then dispelled in the last phase of planetary nebula. We have this gas that have this change that will contaminate the gas and or contaminate the star forming, and have this anti-correlation that we see. Not because we have a reaction that change like in CNO, where you see the carbon with respect to the nitrogen are changed because we move the carbon in nitrogen, but because of the two parallel processes that are working together, one that enhance the sodium and the other, the CnCNO, that deplete the oxygen. And this why we are looking for this reason. This is an interesting cycle just for the actually for the composition, the abundance, not for the production. Another one more clear is directly the magnesium aluminum cycle. Here we are looking for two parts. It's the magnesium is converted is similar to the other with you have two channels at some point, but putting together 4 protons to get an alpha element. But main part is that is the production aluminum. This isotope is not really well stable. Is aluminum 27 that is stable. This one have a mean life of 100,000 years. Then decay with the beta plus decay or electron capture. For the beta decay, you use the beta. For electron capture, there is the eta, just to create more confusion when they're talking about nuclear reaction. The magnesium, it's 24, even number, so it's stable like the neon on the other. This is just if you want the percentage you can find here on Earth. But it's similar. This cycle is produced when you have a senior cycle because it's working at temperature above 30 million. And okay, you have the aluminum in two states, one more stable than the other. One is in the ground state and the other is excited. And the life, as I know, is not so big, little less than 1 million here, but is enough for a star that that produced it when will explode in supernova to leave this aluminum there or in contaminate in other way to with the aluminum. This is why also we check for magnesium aluminum to see how it's changing this ratio, because it's an indicator of evolution in chemistry of the star due the second generation. Okay. See these that are the main most interesting part are, as we saw, are the PP production, the free chain, and the CnCNO. Actually, PP1 is CN because they are two principal reaction. PP2 and PP3 are interesting as collateral, are present, but less. When we start higher temperature, there's a shift in the proton-proton chain from the 1 to 3 to 2 to 3, but in the meantime, CN, CNO are increasing, so they produce definitely less energy than CN and CNO. That, as we saw, have an highest dependence with the temperature. So an increasing with the temperature increase more than PP production energy. After we reduce the helium, we have helium and the start need to go on. So we have this several phases. We need to the helium, it's a higher atomic number, so you need more energy to start. That means you need a higher temperature. That means that start needed to increase its temperature, and we see this is by contraction. And we arrived to the second part, helium burning. Sorry, the camera, I tried to redo the photo, but it's still not focused. It's the helium burning need definitely higher. We are talking about 100 million of temperature, and usually it's representing like 3 alpha in one carbon. But actually, a real the cross section for real 3 or 4 particle reaction is really, really, really small. It's not possible, essentially. We can practically say that it's not possible. In fact, actually, the reaction is a little more complicated. We have an endothermic, because we need like 100 kiloelectron volt, little less than 1 megaelectron volt, and 2 alpha to collide and produce a beryllium-8. Beryllium-8 no, I think, okay. Where? Here. Here, you can see here is given by beryllium-9. Beryllium-8 a little lower, as a lower than helium-4. So to produce beryllium-8, you need energy. It's like with it's here for the iron, and on the other that goes down. Here the beryllium has the peculiar that is the lowest. Oops. Damn it. Yeah. Okay, fighting with the computer. That means that in fact you need you need energy to produce it, and the result is not also well stable. I hope that is right. Yeah. You have production of beryllium-8 that have a really, really, really short time, like 3 to the 10 to the minus 16 second. It die really quickly, but then there is a scatter. But actually, this time is longer than the typical time for collision. So when it's accumulated here, you can have the time to have another collision. It's after a while you have okay, usually this is a typical reaction. The two are fusing, reacting, producing this one, but at the same time you have really quickly scatter and goes back. After a while you have equilibrium among two states, up to you have essentially the quantity, abundance of beryllium-8 effect to the helium-4 is 1 billion. Not so much, but enough. After this, you have another interaction with another alpha with energy and the production of carbon 12 that is this compound that is excited. Luckily, this is a resonant reaction. The fact that it should be resonant was discovered, was supposed mainly, by oil, then discovered by oil because it participated with the several experiments in laboratory to find it, and they showed that it is this kind of energy that I remember. It's the temperature is not so high, so it's the nearby of the kilo electron volt, little less than 1 megaelectron volt, so it's not difficult to accelerate this particle in the laboratory. And they found that there is actually a resonance, so produce is more stable, manage to produce more than it should be. And you have the several channels. One obviously can be the scatter. It's because the carbon emit the alpha, goes back to the beryllium-8, then goes back to alpha element. Or you can have the production to photon on, because you have it's the second excited level. I forgot in English. And so you cannot go directly to the basic one, where you have to drop, so to photon, or directly a production of a pair of electron and positron that will then annihilate, producing the energy. What is interested here? Two things. One, that the Q value is 7, not so much, and if you divide it by mass number 12, you have just 0.6. That means that the energy production by mass is like 1/10 of what is produced by the hydrogen. Using the same core that was produced, you have the star that produce consume all the hydrogen in the core, and will leave you a core of helium. Then the helium will start to be consumed to produce carbon, and in this case we have 1/10 of the energy. If you look at several evolution track, we see that many usually stars have the same luminosity or higher. That means that the life in helium burning is at least 1/10 of the life on the helium burning and hydrogen burning. Hydrogen burning is the main sequence, and the helium burning is the resultant branch. That means that the time that you have the star spending in the resultant branch is more or less 1/10 of the other. So it's really quicker. It definitely is more probable to find a star in the main sequence than in the evolved state. Other things really interesting is that the energy production goes with the square of the density. If you remember, this is also because the electron shielding start to be really more effective. So we enter also the density from the electron shielding. But if you see the exponent calculated as remember before, you get you approximate the progression in this way with the temperature to elevate to the 43 divided the temperature in hundreds of million. So it's 1, 2. So this means that this exponent is among 20 and 30. It's really, really well dependent. The density is really high because star need to increase just by gravitational collapse, so contraction, the temperature, and you have see this high density with a temperature that at the beginning is the lowest, 100 million, means that the gas goes in the degenerate part, and we have something that produces a lot of energy with increase a lot the production energy with a small amount of temperature. That means that since the gas, if it degenerates, doesn't react quickly to the temperature, we can have a really quickly a really increase in temperature inside, so a really enormous increase of the energy, and this is what causes an explosive burning of the helium. Luckily, the gas is degenerated, so part of the energy goes to break the degeneracy, because you need to bring all the electron at higher energy, and it's absorbed, so then the start doesn't suffer. Actually, you don't see, as we see, when the start to burn the helium, actually shrink, decreases in luminosity. So you don't see the explosion is inside. It's called the helium flash. All this flash is absorbed internally, and star keep living. Other substantial reaction for the helium is this one. Yeah, okay. It's the production of oxygen, and if you consume the carbon with the helium and producing oxygen, this is obviously when you have enough carbon inside. The production is not so big, little lower than producing carbon. Then the oxygen can react with even with the alpha particle helium nuclei to produce a neon, and energy production is lower, but this is a really small cross section. That means it needs a higher temperature. So you need a higher temperature to consume this oxygen, and then the neon, and produce the magnesium, produce a little more of energy. If the stars is enough massive, so have a production of CNO, In the core, you have directly the result of the product of the CNO and of from magnesium and the neon sodium cycle, magnesium cycle, and can have also this reaction. Here, as I put, it's the main interesting part that they are producing neutrons. These reactions are a nice production of neutrons that we'll see later are important for another set of reactions. Yes, stop. Come on. Oh, okay. Share. Here, just showing the mass fraction of the two when you are respected to the quantity of helium, mass fraction of the helium, that's the remaining. At the beginning, you are consuming the helium just for the carbon. When you have enough carbon, start to produce of oxygen, and after a while, you have the decrease in carbon and increase in oxygen. Then the exact amount of carbon oxygen you cannot, it's not well clear, but in 50-50 or 20-80. Depend on when stop how is it produced, because while the hydrogen burning produce a core of helium, the helium burning produce a core of carbon oxygen that is mixed. It is not for carbon. Another point I wanted to show. Here you can see it's the same as before. The reaction on the two cycle mentioned, and how is the two cycle one with the line that are changing, and with temperature that we have increase of the sodium, with the consumption of the hydrogen here and the temperature here. So you can see that above a certain temperature we have definitely an enhance of the sodium respect to the normal, and then that we can see later. Okay.
Profe, ¿puede volver a mostrar ese gráfico?
Okay. Oh, just that I'm losing myself.
Bueno, no importa, lo puedo ver después, porque esto está en el libro ese. Porque hay bastante información ahí que no.
No, but this information is additional. It's not that you have to remember, it's just that you have to remember there are some actual here. You are seeing it? This is okay. This in I should have sent it by mail. That is a support material, not material that you need to study. It's just that if you want to check, that can be interesting. Also, the big interesting because up to now you have a lot of here about for apogee and the others, the oxygen sodium correlation, anti-correlation, and the correlation anti-correlation with magnesium and aluminum. You can here, and that is why I just show it. It's obviously you need also to understand what are the parts that are important and what is not important. This is a course about stellar structure and evolution. It's really complex, takes a lot of things. It's for undergraduate, so it's not that you know everything perfect. I just giving you some information that it's useful, it's something that maybe you also hear. I know that at least the two of you hear. Oh, la Macarena dropped. Oops. And so this just to show you. It's not that they are essential to know this one, but you can see this change just to show you.
Okay, thank you.
Not at all. Now let's see if I can. Okay, stop directly. Going back. Just last things about oil. Decide, cioè, suppose it was in resonance, because if you're not considering the resonance with a normal cross section, there will be not enough carbon as we saw in the universe. So essentially, not will be light. There will be so much carbon. This resonance permitted to have a really good production of carbon for enough time to have the composition we saw now. And now we are entering in the dead series of reaction, because the carbon burning that need a higher temperature, 6 to 7, is essentially the end of the start. When the start started to burn the carbon, its life will end with in core collapse. So probably supernova, not 100% sure, but now we have so there are some stars that just collapse with no supernova. But this is the first, the helium is the last safe reaction. Carbon burning is the first that will degenerate in other terms, but will bring the stars to the death. And you see, in fact, definitely, it's the carbon burning started like 1,000 years before the core collapse. When started, then it's near. Not this is not okay. This is for small star, not for not all the stars. Obviously, the massive this part is shorter because they are quicker. The even higher luminosity, so the part is even quicker. But you have less than 1,000 years before the collapse, when you started the carbon burning, that has this several The one with the radiative capture is not so probable, at a really small cross section. The two main reactions, the main channel are this one that you see the production energy is definitely small. You see the number is 20, so you have 12 by 20, so it's 0.2, 1/3 of the helium. So the life here is 1/3 of the helium burning. The most important reaction also, the other, these are the mean, the product, where the reaction goes. But the other also is important because you have a production of alpha particle in this reaction, proton here, that means hydrogen, again, that can enter in other reaction. Neutrons that are important later, we see later. And a decay, it's actually it's going instead of not a decay, but with oxygen with two alpha particles. And these two are losing energy, actually, are absorbing energy. The coefficient is 37, more or less, so it's dramatically higher. The neon burning arrive a little less 1 billion Kelvin. Not really important by energy, you see, you're losing energy. But it's important for the product because the neon, with the, you have the photon disintegration, association, and you have production on oxygen and alpha, or this part, it is the opposite of this one. Here it produces the neon and emitting an alpha. Here the alpha collide with the neon 20 and produce a magnesium that was this one. This can happen. And then with another alpha going to silicium. Or you can have the burning directly of two neon that is not so easy, and the production actually of is like more like a fusion, at a fusion, because the two are splitting into atoms, big atom, oxygen and magnesium. I forgot the G. The next that produce energy and change more is the oxygen burning, but needs a higher temperature, 1.5 billion. So before you have a little neon that subtract a little energy with the contraction, goes to the oxygen. Oxygen, as I said, it's Z is even 8, N is even, because other 8 in total, you have the mass number of the 16 is really stable. The nucleon doesn't accept really easily another alpha or the fusion among them. So you need higher temperature to arrive. You see, less than 1 year before the core collapse. The dependence of them with temperature is not high, it's terribly high. Is like the coefficient is 59. You can have production of sulfur, phosphorus, sulfur again, or silicium. Also, you have this other kind of reaction internally that go from oxygen to phosphorus and silicium, oxygen with another oxygen produce magnesium and then silicium, or the direct production of silicium and an alpha. As before, This is also important to produce proton and neutrons. You see, these are the two main. 60% goes in this part, and 40% are going in this part. But the other, for example, this one is nice because nice. Have a certain important to produce neutrons or produce alpha particles. After this one, you have the end of everything, and there is the silicium burning. Actually, it's more a destruction of silicium because we start with the silicium photodisintegration. At 3 billion Kelvin, you have a photodisintegration, and that you can see here. The silicium arrives a photon, emit an alpha, magnesium, again, photodissociation, neon, and so on, cascade up to the carbon that is destroyed in alpha. You produce a lot of this alpha, 7 alpha with 1 silicium, and then with the little energy, the energy to destroy the silicium, and then going back from silicium, sulfurous, argon, calcium, titanium, chromium, iron, and nickel. The actual production of the silicium is nickel non-iron. The production energy is definitely small, less than 0.2, less than before. And you see that is when start to burning the silicium, it's just 1 day before 100th of the few days before the core collapse. When I start this one, the star collapses, and in star really massive stars, they can last hours, 1 hour, like this class. The production on iron, if there is a equilibrium here, because we have the destruction of the silicium in this way, then production of this way, so there is a certain equilibrium with production of the several elements. Mainly, the production on iron actually is later when the stars collapse, explode the supernova. There are again this reaction, the production of nickel, and the nickel then decay, absorbing electron in cobalt, and then cobalt in iron, and producing energy. This reaction is the last one. Okay, we saw that when we are of the family of the iron, then the fusion is not more exothermic, is endothermic, it's absorbed. So here already it's producing small amount. When start the following step, the core doesn't produce more energy. It's absorbing energy. That means you have not more the radiation pressure. That is, as we saw, is an important part of the pressure, total pressure. So you have essentially that the pressure is dropped dramatically. So the hydrostatic equilibrium, we'll see that will stop to beam, and we have the core collapse of the star. That bring, we've seen star evolution to the supernova. Another part, when quickly, at 7 billion of Kelvin, we have the photodisintegration of iron, little evaporation of iron. And higher temperature, we have the photodisintegration of helium. This can, maybe it's more in the explosion of the supernova, because it's not more possible to increase and production of this material. quickly I show this part. There are two other main processes. There are the S and the R process. Rapid, slow, and rapid. They are connected with two reactions. Neutron capture. We have an element that captures a neutron, so just increase its mass number and emit a photon. Or we have beta decay, beta minus or beta. We have an element with mass number A and atom number Z that decay, emit an electron, so we have a neutron decay. So we have not one neutron inside one proton mass. So the atomic number increase one, we are going to the next. And while the mass number is the same. If the velocity of the neutron capture is higher, the beta decay, we have a rapid R process, rapid process. We see as the time, mean time of the process. Or if the velocity of the neutron capture is lesser, the velocity of the decay, we have an S process, a slow process, because the neutron capture happen in really longer time, so you have time for the beta decay. This will cause the production of all other material. That bring to this the famous nu from the observation of the neutron merging with neutron stars. We have the several reactions. You can have okay, hydrogen and helium is produced by the composition and the Big Bang. The production of the other massive stars. This is the result inside. Then merging neutron stars, we have all the other elements. They are produced with the R, the slow and the rapid neutron process with the neutron capture, because the neutron stars are destroying themselves and throwing neutrons all around, and so you have this to process really quickly and can produce all the other. And this is how we produce essentially what is really nice, gold and platinum that are here. That before we thought we should be exploding massive stars and exploding white stars, essentially exploding white star dwarf here, the supernova of 1A, and then we realized that. Also because we observe it directly in the composition. Oh, good. Okay, we finish. Next week we'll start, I think, to work with studying how star is behaving mathematically with the evolution, with the internal part, studying how it's working, the model, polytropes, stability, and so on. Any question?
No.
Okay. Stop sharing. See you next week.
See you next week.